Piping vibration pulsation, understanding causes and effects in piping systems. Introduction to pulsation in piping systems, significance and mechanism of pulsation. Pulsation refers to dynamic pressure fluctuations within a fluid system that occur at discrete frequencies, often resulting in tonal excitation. These fluctuations can amplify through acoustic natural frequencies of the piping system, creating standing wave patterns that significantly increase pressure amplitudes. When these amplified pulsations coincide with structural natural frequencies of the piping, severe vibration and fatigue failures can occur. Pulsation is particularly critical in oil, gas, and petrochemical facilities where high-pressure systems and complex piping geometries are common. Understanding pulsation mechanisms is essential for preventing catastrophic failures, minimizing downtime, and ensuring compliance with safety standards. Acoustic natural frequencies depend on pipe length, diameter, and fluid properties such as density and molecular weight. These frequencies can shift with changes in operating conditions, making proactive design and monitoring crucial. The interaction between excitation frequency, acoustic resonance, and structural response forms the basis of pulsation-related vibration problems. Pressure pulsation generation and impact, reciprocating or positive displacement pumps and compressors. Reciprocating and positive displacement pumps and compressors inherently generate oscillating pressure fluctuations due to their cyclic operation. Each stroke or displacement event introduces a pressure wave into the fluid system, creating tonal excitation at the machine's operating speed and its harmonics. These pulsations can be amplified by acoustic natural frequencies within the piping, resulting in high dynamic pressures and shaking forces at bends, tees, and reducers. When structural natural frequencies of the piping coincide with these amplified pulsations, resonance occurs, leading to severe vibration and fatigue damage. API standards such as API 618 for reciprocating compressors and API 674 for reciprocating pumps mandate pulsation analysis to predict and mitigate these risks. Common mitigation strategies include pulsation dampeners, acoustic filters, and careful design of piping geometry to avoid resonance. Failure to address pulsation can result in cracked welds, damaged supports, and catastrophic leaks, emphasizing the need for thorough analysis during design and operation. Rotating stall phenomenon and its effects, centrifugal compressors and rotating stall. Centrifugal compressors can experience a flow instability known as rotating stall, particularly at low flow conditions near the surge line. Rotating stall generates tonal pressure pulsations at subsynchronous frequencies, typically between 10% and 80% of rotor speed. Although these pulsations may not significantly affect rotor dynamics, they can excite acoustic natural frequencies in the discharge piping, leading to amplified pressure fluctuations and vibration. The susceptibility to rotating stall depends on impeller geometry, operating speed, and process conditions. If acoustic resonance occurs, the resulting vibration can damage piping, supports, and small bore connections. Preventive measures include maintaining adequate flow margins, implementing effective anti-surge control systems, and conducting pulsation analysis during design. Understanding rotating stall is critical because its occurrence can be intermittent and highly dependent on operating conditions, making real-time monitoring and predictive modeling essential for reliability. Periodic flow-induced excitation, mechanisms and examples. Periodic flow-induced excitation occurs when vortices are shed from components in the fluid stream at specific frequencies determined by the Strouhal number, fluid velocity, and characteristic dimensions. Common sources include dead leg branches, flow over protruding components, and thermal wells or probes inserted into the flow. For example, flow past the open end of a dead leg branch can generate tonal excitation similar to blowing across a bottle, producing discrete frequencies that may coincide with acoustic natural frequencies of the branch or main line. Thermal wells are particularly vulnerable because vortex shedding can excite their structural natural frequency, causing them to vibrate like a tuning fork and fail due to fatigue. While these mechanisms rarely cause failure alone, they can interact with other excitation sources to produce significant vibration. Preventive measures include proper design of thermowells per ASME PTC 19.3, minimizing dead lags, and ensuring separation between excitation and natural frequencies by at least plus or minus 20%. Impact on piping integrity and preventive measures, consequences and mitigation strategies. Pulsation-induced vibration can lead to high cycle fatigue failures in piping systems, particularly at welded joints and small bore connections. Consequences include leaks, environmental hazards, production downtime, and costly repairs. Mitigation strategies focus on both excitation and response control. On the excitation side, pulsation dampeners, acoustic filters, and flow conditioning devices can reduce pressure fluctuations. On the response side, increasing pipe stiffness, adding supports, and avoiding resonance through design modifications are effective. Advanced predictive techniques such as acoustic finite element analysis and pulsation modeling help identify potential issues during design. Industry standards like API 618 and API 674 provide guidelines for pulsation analysis and control. Regular monitoring, visual inspections, and vibration measurements during operation are essential to detect and address emerging issues. A proactive approach combining design best practices, compliance with standards, and ongoing maintenance ensures long-term reliability and safety of piping systems.